Welcome to Dr. Boxy Teaches Electromagnetism. In the previous lesson, we looked at vector components and how to work with them. Take a look now back at the Maxwell equations, the ones you see written here next to me. Do you see that weird upside down triangle there? And the rounded D in the third and the fourth equation? Well, these are special kinds of derivatives. In this lesson and the next one, we will look at differential calculus, and more specifically, at differential calculus of scalar and vector fields. To start with, we will introduce what the word field actually means. Do you see the E and the B in the equations? Well, these are the electric and the magnetic field, and they are instances of such fields. So let us get started. So what is a field? Imagine I asked you what the temperature of a room was. You could answer that the temperature is, for instance, 20 degrees centigrade. But in the back of your mind, you're probably aware of the fact that a temperature is not literally 20 degrees at every single point in the room. Some parts of the room may be a bit cooler, others may be a bit warmer. When we say that the temperature is 20 degrees, what we mean is that averaged over the whole room, the temperature is 20 degrees. But what if we were to look at the temperature at every single point in the room? So for instance, this point here may be at a temperature of 21.1 degrees. And so what I would do is I would write at this point in space the number 21.1. I take some other point in the room, this one, and at that point the temperature could be, for instance, 19.6 degrees. And so I write the number 19.6 here. And I do that with every single point in the room. What I'm doing is, in my mind, filling the whole space in the room with numbers. That is a field. A field is simply filling up space with something, and in this example, we filled it up with numbers or scalars, which is why it is known as a scalar field. What we've done mathematically is introduced a function, which I call capital T in this case. It takes as an input three numbers, the x, y, and z components of the point we are considering in space, and what comes out is one single number representing the temperature at that point. So this is a scalar field. But we could also look at vector fields, where we draw a vector at every point in space instead of filling in a number. So for instance, think of the motion of the molecules around me in the air here. I take a point in space, there is a molecule of air here. I could represent its motion by an arrow. The direction in which the arrow point is the direction in which that molecule is moving at this point in time. And the magnitude of the arrow tells me how fast it is doing that. And I can do that with every single point in space, which would fill up space with arrows, with vectors, which is why this would be called a vector field. Mathematically, in this case, we again introduced a function, this time a vector function. The input is, once again, three numbers, the x, y, and z coordinates of the point we are considering. And what comes out are the x, y, and z components of the vector at that point. Notice that I wrote the vector as a column, while in the first lesson I said that we would write vectors as rows of components. So the vector A can be written as AX, AY, AZ, and this time I wrote it in a column, and I just wanted to point out the fact that for our purposes in this course, they will mean exactly the same thing. There are contexts in which we want to differentiate between vectors written as a row and written as a column, but for us they mean exactly the same thing. It's just a matter of notation. So this is a field. What can we do with them? We want to be able to calculate derivatives of such fields. But before we do that, let us remind ourselves what the meaning is of derivatives for functions of one single variable. So if we start with a function f of x and we choose some point on the x-axis, let's say x0, what is the meaning of the derivative at that point? Well, one possible interpretation of it is the slope of the function at that point, or more precisely, the slope of the tangent line at that point, the slope of the green line. But another possible interpretation is it tells us how much f changes when we increase the input x by a very small amount. What we mean by that is the following. We start at the point x0, we plug that into f, and what we get is f of x0. We then take another point on the x-axis, slightly larger, let's say x1, and it is a distance of delta x away from x0. Plugging that into f gives us f of x1, which is a distance of delta f away from f of x0. The derivative relates delta f with delta x. Specifically, it tells us that delta f is equal to that derivative times delta x. In this specific sense, The derivative tells us how much f changes per change in x. Now, this is only an approximation. It becomes better as delta x goes to 0. So as we take the limit of x1 going to x0, this approximate equality will become an actual equality. And as delta x goes to 0, we get this equality where, remember, dx and df mean infinitesimally small changes in x and in f. Now, for the mathematical purists among you, this is not exactly well defined because df and dx are vague things mathematically in this context. But there are ways to interpret this equality which is very rigorous and precise from a mathematical point of view. One way to do it is the following. We take the function f of x and we think of x as a function of some other variable t. And what we want to do is to take the derivative of f with respect to t. The chain rule tells us that the derivative is equal to df by dx times dx by dt. Now, we write those things as fractions, df divided by dt, but it is not actually a fraction, it's just a notation for the derivative. But it is a useful notation. And if we take the notation seriously for a second and get rid of the dt's on both sides, we get exactly the equality we found above. df is df by dx times dx. So, in this sense, we can think of this expression, df is equal to df by dx times dx, as something that still needs to get a dt in the denominator such that you get an expression for the derivative in the sense of the chain rule. There's also an alternative way of interpreting that same equality, but using integrals instead of derivatives. We can take this expression, so we take the integral of df, we think of f as being the variable in this case. Well, if we integrate df, we get delta f. But if we go again with the integral of df and we apply a change of variables, we apply the substitution rule, we get an integral of df by dx times dx, where we changed from a variable f to a variable x. Now, if we get rid of the integral signs in this case, we get again that same expression. So another way of interpreting it, which is mathematically correct, is to say that what is written there is something that actually should go in an integral. If you put a snake in front of each of those expressions on the left and the right hand side of that equality, you get a statement which is mathematically rigorous. No matter which interpretation you want to use, we will always think of it as dx is a small change in x, df is a small change in f, and the derivative tells us what the relation between them is. In order to generalize the expression we found on the previous slide to functions of multiple variables, we start with something known as the partial derivative of a function. So we consider again that function which represented temperature. In general, t can represent any function taking 3 inputs in this case, but let's think of the temperature to have a clear image in mind of what we mean. And we look again at the temperature at the room, and we choose some point, let's say the point with coordinates 1, 1, 2, and the temperature at that point is 19 degrees. We want to know what happens to the temperature, how much is the change in the temperature if we move away from that point. Now, moving away from a point, if we have a function of just one variable, moving x, changing x, can only either increase or decrease it. So on the x-axis, it means we can either go to the right or to the left. But if you have a function of multiple variables, there are infinitely many directions in which we can move away from a point. So we need to make choices about where to move to. Now, there are 3 special directions for a function of 3 variables, namely the directions of each of the coordinates of the system. So in this case, we can think of moving only in the x direction, a small distance dx, and not changing the y nor the z component of the position. In that case, we look at how t changes when only its x input changes and y and z remain constant. The derivative that represents how much t changes when only its x input changes is written as this rounded d, dt by dx with a rounded d, and this is known as the partial derivative of t with respect to x. We can do something similar in the y direction. If we move only in the y direction, then we get a partial derivative of t with respect to y, and similarly dt dz. Now, how do we calculate something like that? Well, as an example, let's look at the function x squared times cosine y plus z. Calculating dt dx means we keep y and z constant. We treat them as if they were constants. And so we have x squared times the cosine of some constant plus z. Taking the derivative of that with respect to x gives us the following. The derivative of x squared with respect to x is 2x, and it is multiplied by some constant cosine y, which just remains there. So we get 2x times cosine y, plus the derivative of z with respect to x, which is 0. Then the derivative of t with respect to y, we treat x and z as constant, so the x squared just remains, multiplied by the derivative of cosine y with respect to y, which is minus sine of y, plus the derivative of z with respect to y, which is 0. And finally, dt dz, we treat both x and y as constants, meaning that if we take the derivative of the first term, it vanishes, and we're left with the derivative of z with respect to z, which is simply 1. What we see is that calculating partial derivatives is fundamentally not different from calculating derivatives of functions of one single variable. What we do is actually treat it as if it was a function of one variable, and we treat all the other variables in this context as constants. These are partial derivatives. We want to generalize the expression we found for df, for the change in f a couple of slides ago, to functions of multiple variables. So we take again the function capital T, which takes as an input x, y, and z. Now remember that one of the ways we could interpret the statement we found above was by using the chain rule and getting rid of the dt's in the denominator. So for that purpose, we will think of x, y, and z, all of them functions of some variable t. And we want to find the derivative of capital T with respect to small t. Now, the chain rule for functions of multiple variables takes this form. The derivation and the proof of this theorem will be left for another course. There will be in the future a course on vector calculus, and in that course I will discuss this theorem, prove it, and explain exactly where it comes from. But for now, this will be taken for granted, and we will work with that. Notice the use of the partial derivatives there. Notice also that if we think of the function as only a function of x, so we get rid of the terms with the z and the y, the second and the third term just vanish, we are left with the derivative of capital T with respect to small t is the derivative of t with respect to x times the derivative of x with respect to t, which is exactly the chain rule for functions of one variable. So what we get is a generalization of that. And if we get rid of the dt's now in the denominators, we find this expression, which is the generalization we were looking for. The interpretation of this statement is that if we start at a point x, y, z and we move away from it, the change in t is a sum of three changes, one due to the change only in the x direction, plus the change only in the y direction, plus the change only in the z direction. That is the expression we were looking for. How do we use it now? We want to rewrite the expression for dt. So to do that, remember dt represents the change in t when we move away from a point. Now the motion away from that point is represented by a tiny displacement dl, which is a vector whose components are dx, dy, dz. And we saw that dt is given by this expression. Now think back to one of the expressions we found for the dot product of two vectors. We saw that a dot b can be calculated as ax bx plus ay by plus az bz. The expression we found for dt is similar to that expression. It is of that same form. It is specifically of that form if we take as vectors for a and b the following two vectors. As a, the first vector, we take a vector whose x, y, and z components are the partial derivative of the function capital T. And as b, the second vector, we take dl, the vector whose x, y, and z components are dx, dy, dz. If we work out that dot product using this formula, we get exactly the expression we found above for dt. Now, these two vectors get a name. The second one we already saw. It is dl. The first one is written by the upside down triangle with the function t after it. It is known as the gradient of t, and it is a vector whose x component is the partial derivative of the function with respect to x, its y component is the partial derivative with respect to y, and its z component is the partial derivative with respect to z. Notice that we introduced that upside down triangle now. We will see in a couple of slides what the exact meaning is. We encounter now this upside down triangle, but it is not exactly the way in which it is used in the Maxwell equations. We will see how it is used there in a couple of slides. So this is the concept of the gradient, and we want to understand the meaning, the physical interpretation of the gradient, and we want to see how to calculate it. To interpret the gradient, we start with the expression we found for the gradient itself and for dt. Now we have two different ways of calculating dot products between vectors. One of them was the expression we used on the previous slide, and another one was AB cosine alpha. If we use that one on the dot product we found for dt, we get the expression that dt is equal to the magnitude of the gradient times the magnitude of the displacement dl times the cosine of the angle between those two. Now, we can use this to interpret what the gradient actually means. If we fix the size of the displacement, so we fix the distance we're moving away from our initial point, and we're asking in which direction do we need to move, in which direction does dl needs to point, such that the change in t, the increase in t, will be maximal. Well, the answer is it will be maximal when the cosine of alpha is 1, which is the largest value a cosine can take, and that is the case when alpha is 0 degrees. So that means that the increase in t is largest when the angle between the displacement and the gradient is 0. In other words, when the displacement is in the direction of the gradient. But that means that the gradient always points in the direction in which t increases most steeply. So that is the meaning of the direction of the gradient. What is its magnitude? Well, if we are moving in that direction, meaning that alpha is 0 such that the cosine of it is 1, we get that dt is equal to the gradient of t, the magnitude of that, multiplied with the magnitude of dl. And that means that the change in t, dt, is equal to the magnitude of t per dl. So this is the generalization of what we saw before for derivatives of functions of one variable. The derivative told us how much the function changes per change in the input x. Well, here, the gradient tells us how much the function t changes per change in the position we are sitting at. And so in that sense, the direction of the gradient tells us in which direction it increases most, and the magnitude of the gradient tells us how much that changes if we move in that direction. Let us look at contour lines on a map. So think of some contour lines on maps of mountains. So these are lines of constant altitude on a mountain. So here is a line of a constant altitude which is higher than the outer one. This is a line of even higher altitude. This can be the peak of the mountain. And what we're looking at are lines of constant height h as a function of x and y, of the position we are standing on. What we want to have is at every point on the map an arrow that guides us in the direction in which the increase in altitude is most steep. So for instance, at this point, if you want to increase the height most steeply, you would have to walk in this direction. At this point, you would have to walk in this direction. So what we have is the gradient of h. And notice h itself is a scalar field. It's the height at every point. There is a number at every single point corresponding to the height there. The gradient of that height is a vector field. There is a vector at every point, which is always directed towards the direction of steepest ascent, and the magnitude tells us how steep the ascent is at that point. So the input of a gradient is a scalar field, and the output of a gradient is a vector field. As an example, we want to calculate the gradient of this specific function r. What does it represent? Well, if we take a coordinate system, x, y, z, what this function represents is the distance from the origin. So at every point in space, we can write a number, and that number represents how far that point is from the origin. So it would represent this distance here. Notice that this can be rewritten as x squared plus y squared plus z squared to the power 1/2. The gradient of this r is a vector whose x component is the partial derivative of r with respect to x, its y component is dr dy, and its z component is dr dz. For the first component, dr dx, we calculate it, we get the 1/2 that is in the exponent comes down, so we get 1/2, multiplied by the whole bracket x squared plus y squared plus z squared to the power minus 1/2, multiplied by the inner derivative because of the chain rule, which is 2x. And notice that the 1/2 and the 2 cancel out, so we're left with x divided by the square root of x squared plus y squared plus z squared. Similarly, if we were to calculate dr dy, you would get y divided by that square root, and dr dz would be z divided by that square root. Taking all of this together, we find that the gradient of r is a vector, and it can be written in the following way: x divided by that square root times x hat plus y divided by the square root y hat plus z divided by the square root times z hat. And if we put everything on one denominator, one common denominator, which is the square root of x squared plus y squared plus z squared, and in the numerator we get x times x hat plus y times y hat plus z times z hat. Now at the end of the previous lesson, we saw that this vector, the one we have in the numerator, is the vector r itself, representing a vector that goes from the origin to the point in question, and the denominator is the magnitude of that vector. So we have the vector r divided by its magnitude, and if we divide a vector by the magnitude of that same vector, we get a unit vector in that direction. So what we get is the unit vector r hat. Now, what does this tell us? It tells us that the direction in which r, the distance to the origin, increases most is the direction of r itself, meaning away from the origin. So if you want, wherever you are in space, if you want to increase the distance to the origin most steeply, you have to move away from the origin. That sounds reasonable. And the fact that it's a unit vector tells us that if we move in that direction a distance of 1, the increase in that distance will be equal to 1. That is patently, crushingly reasonable. This is the way to calculate gradients. This is specifically the gradient of this function. To interpret the upside down triangle, we start with the expression we have for the gradient of the function t. And instead of writing dt dx times x hat, I just write it as x hat times dt dx. All I've done is change the notation 3b to b3. There is absolutely no difference between them. It's maybe a bit weird to see the scalar after the vector, but it's just a question of notation. They mean exactly the same thing. Now, if we take the capital T, which is common to all three terms, and we simply pull it to the end, we get the expression I wrote now. And you should think of the ddx, ddy, and ddz as operating on whatever is after the brackets. The thing within the brackets is what we define to be that upside down triangle. It is known as the del operator or the nabla operator. There are two different names for the same thing. And we will treat this del operator as a vector whose x component is ddx, y component is ddy, and z component is ddz. But you should keep in the back of your mind that it is not really a vector in the sense that we're used to. ddx is not a meaningful thing. ddx is meaningless unless you plug a function into it. df dx is the partial derivative of the function f with respect to x. ddx as such doesn't have a meaning. So because of that, it's known as an operator, and it only gets meaning once it operates on a field, on a scalar field. Now, notice also that we write it as the del operator with a t behind it, so it looks as if it was a multiplication of two vectors. Sorry, it looks as if it was a multiplication of a vector with a scalar, but it's not actually a multiplication. We use the notation of multiplication, but it is actually an application of the operator on the field. Now we had three different kinds of multiplication, and they will give us three different kinds of derivatives that we will need. The first one is the multiplication of a vector with a scalar, and if we use that, but instead of taking a multiplication, we actually take an application, we apply del to t, we get what is known as gradient, which is what we studied now. But there were two other kinds of multiplication. There was the dot product, and if we treat del again as a vector, but instead of multiplying it, dotting it with v, we use the same rules as we used for dot product, but by applying it to a vector field v, we get a new kind of derivative known as the divergence. And if we use the rules for the cross product, we get again a new kind of derivative of vector fields known as the curl. In this lesson, we looked at the gradient. In the next lesson, we will look at the meaning and the calculation of the divergence and the curl of vector fields, and we will also learn what the differentiation rules are for each of those derivatives. I'll see you next time.